Okay, guys, let's dig into some example problems to start to show you how you can make use of Newton's laws. So the first situation that I want us to consider in this video gives us an opportunity to connect with some of what we just talked about in the last video in terms of the normal force. So I want you to imagine a block again, uh, and for the time being, assume that this is some sort of like frictionless, uh, very slippery surface. We'll talk about friction in the next chapter. And we're imagining there's some pulling force here that has a magnitude of 40 newtons. And if I can draw an N. And this angle theta is going to be 30 degrees. The block has a mass of 10 kilograms. And the questions that we're interested in answering are, we want to find the acceleration of the block, and we want to find the normal force. Okay, so let's flesh out this diagram with our forces. So make this into, imagine a free body diagram. We would have the weight pointing down. We would also have the normal force pointing up. And you can see we're going to have to solve this problem, break this pulling force into components. So there would be, we could call this, for example, FPX, and then there would be a vertical component, FPY. And just to sort of review that concept of how you decompose a vector like that into components, notice that the x component of the pulling force will be Fp cosine theta, and the y component of this will correspond to Fp sine theta. And remember, you can convince yourself, or you can check yourself with this. Imagine that this angle theta gets smaller and smaller, right? In that case, the pulling force would be totally along the x direction. Forgot to put my coordinate system in. If it's along the x direction, that means that Fpx should have the same magnitude as Fp, the pulling force. And what trig function would give you, 1 as the angle gets small? Well, that would be the cosine. So you can use that sort of technique to check and get confidence that your trig functions are set up correctly. So next, let's look at the sum of the forces in x and the sum of the forces in y. So actually, let's look at y first. Well, we'll find the acceleration first. So let's look at the sum of the forces in the x first for part A. So what will we have? We'll have Fp x, i.e. Fp pen here. On pen. Second. So we would have Fp cosine theta, positive, pointing to the right. And notice that is actually the only component force that we have in the x direction. So this would equal the mass times the acceleration. This is, of course, remember Newton's second law. Now we're dealing with a situation where this thing is not at rest. It's going to move. So we could solve this for the acceleration. Fp cosine theta divided by the mass. We can put in our numbers here. 40 newtons times cosine of 30, 10 kilograms. And when we crunch the numbers here, we would find that this gives us 3.46. Let's give ourselves the right number of significant digits. 3.5 meters per second squared in the I hat direction, so along the x axis. And so that's the acceleration calculated from the force and Newton's second law. So that's to A, part A. And then to B, we can look at the sum of the forces in the y direction. So what are we going to have? We would have the normal force. We would have minus mg. And then notice we also have this Fpy. Now, this is going to equal the mass times acceleration in general, but this will be 0 because it's not accelerating in the y direction. We can then solve this for the normal force. Substitute in what Fpy is. Fp sine theta. And let's put in our numbers here. So this would be 10 times 9.8 minus 40 sine 30 degrees. And we would find that this is 78 newtons. And notice this is pointing in the j hat direction. And note, like the other questions that we had looked at, this is the normal force is actually less than the weight in this situation because there is that component of that pulling force that's directed up. So it's pulling it up a little bit, and so reducing the normal force. Because remember, the normal force is this component force. It's supplying whatever is necessary to keep that object at rest in that direction. Okay, so that's an example that's tying in what we had talked about with the normal force, but also now it's allowed to accelerate. Let's look at a couple more. Okay, so this example that I want you to see will give us an opportunity to connect with kinematics that we talked about a couple chapters ago. And the question is, what average force is required to stop a 950 kilogram car in 8 seconds? The car is traveling at 95 kilometers per hour. Okay, so let's give ourselves a cartoon of this situation. We have a car. It's going at 95 kilometers per hour. Give ourselves a coordinate system. And this thing has a mass, evidently, of 950 kilograms. And we want to know the force. So we know that the force, the net force on the car, will equal its mass times acceleration. So if we can find the acceleration, we have the mass, so we would be able to find the force. So in other words, find A, find the force. Okay. And in order to do this, notice our acceleration. We need a change in velocity per change in time. And normally with the change in time, we're just assuming that we're counting up from 0. But this final velocity would be 0. So the velocity that we start with divided by the time, the 8 seconds. Now notice 95 kilometers per hour is sort of a weird unit. We're going to need to convert that kilometers per hour into meters per second. So let's do that first. Kilometers per hour. So there are all, there's different unit conversions that you can use. We know that in 1 kilometer, there's 1,000 meters. And we also know that in 1 hour, there are 60 seconds times 60 minutes. So there are 60 times 60 seconds. And put it like that. So there are 3,600 seconds, in other words, in an hour. So if we employ these unit conversions, we would have a number that's in meters per second. And when we crunch those numbers, we find this is 26.4 meters per second. And so let's find our acceleration. We're going to have negative 26.4 meters per second in 8 seconds. Negative because we're subtracting it. As in our cartoon, we have this going to the right in the positive x direction, so it would be positive. But since we're subtracting it, that becomes negative. And when we divide that, we would see that be very close to negative 3.3 meters per second squared. And according to the cartoon, how we have this set up, this would be in the I-hat direction. Okay, so if we know the acceleration, we can find the force. The net force is the mass times the acceleration. So, which is simply going to be 950 times our 3.3 per second squared. And this would be negative 3,100 newtons. And notice the force is in the same direction as the acceleration, so this would also be in the I-hat direction, as we have it depicted in this sketch of the problem. And I think this is a good problem. It shows you connecting to stuff from kinematics, as well as kind of making the point that it's really useful to draw a picture. So we didn't have a picture provided in this question, so we created one. Let's look at another question. This gives us an opportunity to revisit the normal force. So here's the question I want us to think about. We have a box weighing 77 newtons, rests on a table. A rope tied to the box runs vertically upward over a pulley, and a weight is hung from the other end. Determine the force that the table exerts on the box if the weight hanging on the other side of the pulley is 30 newtons, 60 newtons, or 90 newtons. So let's give ourselves a coordinate system. Let's label this Call this one M1, this one M2. And we have two objects here, so let's create some free body diagrams. For M2, that one will be pretty easy. We just have this tension force that's pointing up, the object's weight that's pointing down. For mass 1, also fairly straightforward. We're going to have the tension force, again, pointing up. We would have this object's mass, or sorry, its weight, pointing down. And then, of course, we would also have the normal force pointing up. And, one question you may have is, well, how can it be that these tension forces are both pointing up? How does that work exactly? Well, you can think of the pulley, and we'll encounter pulleys in other problems too, as something that's allowing the force to change direction. So that's how, when you're solving these kinds of problems and you substitute in for a tension force from one object into your math about the other, that works because the pulley has changed the direction. Okay, so let's sum the forces. So for both of these, there will not be any forces in the x direction. We can just divide them up like this. So the sum of the forces in the x on mass 2 is 0. But the sum of the forces in y, we're going to have the tension minus the weight. That's going to equal 0 if it's just resting. So in other words, the tension is m2g. And then on mass 1 here, again, there's no components in x. We sum the forces in y, we find the tension minus the weight plus the normal force going to equal, again, this would equal the mass times acceleration for mass 1, but it will be 0 since it's resting on the table. And what this allows us to do is substitute in for the tension. So we can substitute in here. M2g minus M1g plus the normal force equals 0. So we can solve this for the normal force. So the normal force is going to be subtracting those pieces over. M1g minus M2g, or maybe more concisely, g times M1 minus M2. And let's look at our different cases. So, our boxes are listed in weights, so actually maybe it would be better. We'll just leave it like this. The different cases that we have, so for A, the hanging weight, so in other words, M2g is 30. So, and actually, I'll put it on our diagram here. So M1g is 77 newtons, and then M2g is going to equal either 30, 60, or 90. So for those different cases, we can consider this will be 77 minus 30 for A. So that gives us 47 newtons. And that would be, of course, in the j-hat direction. pointing up. And notice this is less than the weight. For B, this would be 77 minus 60. We have 17 newtons. And then for C, we would have 77 minus 90. But this doesn't work. You can't have your normal force supplying more than the weight of the object that's sitting there in this circumstance. It's the table is only going to be able to push back. It can't grab the object. In this situation, if that normal force was negative, that would mean that the box was sticking to the table, which doesn't make sense. So in this case, this would be 0 newtons. And it 0 newtons would mean that the thing starts to accelerate, in other words. So 0 newtons slash starts to accelerate. So I hope this gives you kind of another example, this time except with numbers, of looking at these this idea of the normal force and how it also connects with when you have an object that begins to move. If you no longer have a normal force, you might have a scenario like this where you have an object that's being accelerated upward. Okay.